For this section and the next, for our last two sections out of Chapter 4, we're working with logarithmic functions, using exponential functions to go back and forth, but we're going to be doing less graphing and more algebra. Remember that logarithms are the inverse of exponential functions. This means that the properties for logarithms are going to be related to our rules for exponents. We already know these three rules for exponents. This is not new information. If you can remember these three rules for exponents, it's going to make working with your logarithms so much easier. Our product rule for exponents tells us that when we're multiplying the base, we add the exponents. For example, b to the n times b to the n equals b to the n plus n. An example in numbers, 2 cubed times 2 squared equals 2 to the 3 plus 2, or 2 to the 5th power. And then I can figure out what 2 to the 5th is. Why does this work? Well, 2 cubed, 2 times 2 times 2 is 8. 2 squared is 4. 8 times 4 is 32. And if you plug that into your calculator, 2 to the 5th, also 32. If I multiplied 3 times 2 and got 6, 2 to the 6th is 64. It's not right. So if I'm multiplying the bases, I'm adding the exponents because, again, another way of looking at this, 2 cubed tells me 2 times 2 times 2. That's 2 cubed. Times 2 squared, that's 2 more 2's. So I'm multiplying 2 times itself 5 times. Alright, if I'm multiplying the base, that's my product rule. Product is the answer to a multiplication problem. Quotient is the answer to a division problem. When I'm dividing the base, I subtract the exponents. Multiplication is just repeated addition. Division is just repeated subtraction. So, there's my general case. Specifically, if I have 2 cubed divided by 2 squared, that's 2 to the 3 minus 2, or just 2 to the first power, or 2. We already figured out that 2 cubed is 8, 2 squared is 4, 8 divided by 4 is 2. See, it works out either way. If I want to think about simplifying, 2 cubed is 2 times 2 times 2. 2 squared is 2 times 2. Anything over itself is 1. So that's a 1, and I'm left with a single 2 in my numerator. Alright, my last rule for exponents is the power rule. When we raise an exponent to another power, we multiply those exponents together. This is when we multiply exponents. So in this case, 2 cubed squared is the same thing as 2 to the 6th. We said that 2 to the 6th is 64. 2 cubed is 8. 8 squared is 64. 8 times 8 is 64. And I was trying to think if there's a third way to look at this, and there's not. That's all we got. Okay, those are our rules for exponents. We're going to keep those in mind, and they inform our rules for logarithms because logs and exponents are inverse functions. We're going to use our rules for logarithms to help us expand, that's pull apart and make it more spread out, or contract, condense logarithm statements, and to see if we can simplify any of the expressions when we break it apart or put it together. Our first rule for logarithms is our product rule. Remember your product rule for exponents. Our product rule for logarithms tells me that the logarithm of a product is the sum of the two logarithms. So right here in my argument, if I'm multiplying there, I can break it apart as two log statements. So the argument is m times n. I can break that apart. Both of them are still the same base b, m plus log base b of n. So I separated my two log statements. Now here's how this can maybe help us. For example, if I have log base 5 of 25x, well in my argument I'm multiplying there. That's a product. My product rule says multiplication pairs with addition. So I can break this apart to two log statements, log base 5 of 25 plus log base 5 of x. And this first log statement, log base 5 of 25, well, what is the exponent of 5 that gives me 25? 5 squared is 25. So that simplifies to be 2, which means that when I break it apart, I can simplify it in a way that I couldn't have simplified before I broke it apart. That's my product rule for exponents. No, logarithms, sorry. Quotient rule for logarithms. Quotient's the answer to a division problem. Division pairs with subtraction. So my quotient rule for logarithm states that the logarithm of a quotient is the difference of two log statements. So when I have a quotient in my argument, I can split this apart using subtraction. Whatever's in the numerator is positive, whatever's in the denominator gets subtracted from that. So let's do an example that we can simplify. Log base x of 9 over x. There's a quotient in my argument. Division pairs with subtraction. So I have log base x of 9 minus log base x of x. The log base x of 9, there's nothing I can do with that, but right here, what is the exponent of x that gives me x? Well, that's just 1. So I was able to simplify that statement in a way I couldn't have done the original. All right, our third rule for logarithms, our power rule. Power rule states that the log of a number with an exponent is the product of that exponent and the log of that number. Now that's really wordy and it's a lot, right? So let's go ahead and see. We've got log base b of m to the p power. This power rule tells me I can pull that out front and make it a coefficient. So p times log base b of m. All right, examples are usually better. Let's do one with an example. Let's do natural log of 3 to the x squared. Well, first, I am multiplying in my argument. That's product. Product pairs with addition. So I'm going to split it apart and say natural log 3 plus natural log of x squared. That squared just goes with this x. The 3 is not being squared because the 2 is on the inside, not the outside. Now this, there's not anything I can do here. This, I can apply that power rule, and I can pull that 2 out front. So natural log 3 doesn't change. This becomes 2 times natural log x. And you know what? There's nothing I can simplify there. Sometimes I won't be able to simplify. I'm just expanding. Now these rules that we did expansions with, we are going to apply, work in the opposite direction to condense. But first let's practice expanding. We've got 6 problems here that we're going to expand. We're going to simplify whenever we can. And then we will turn that around and we will do some condensing with our logarithms. Okay, I'm dividing in my argument. Division is a quotient. Repeated division is subtraction. So division pairs with subtraction. Sorry, I had a hard time getting that out. All right, log base 3 of 27 minus log base 3 of 4. And I stop to look to see if there's anything I can simplify. And right here, what's the exponent of 3 that gives me 27? Well, that's 3. So I can simplify that first expression. Okay, let's look at the next one. That is an exponent right there. That x is an exponent, so I can use my power rule. So for this one, I used my quotient rule. For this one, I can use my power rule because it has an exponent. So I'm going to say, okay, x times log base 3 of 9. And then I stop and I look and I say, oh, wow, right there. What's the exponent of 3 that gives me 9? Well, that's 2. So x times 2 is just 2x. We were able to simplify a lot there. All right, for this one, I've got to rewrite that radical as an exponent because I don't know what to do with this radical. Square root 3 is the same thing as 3 to the 1/2. Now that's an exponent, and I can apply my power rule. So 1/2 times log 3. LOG, log with no base written, tells me it's base 10, and I can use my calculator. If you plug this into your calculator, let's round it to 3 decimal places. Do you do log 3 and then take half of that, or do 0.5 times log 3, round that to 2 decimal places? It should come out to be 0.239. Common log 3 times 1/2 or divided by 2. There we go. Alright, let's look at this next one. I've got a quotient there, so we're going to go back. That is our quotient rule again that we're going to apply. Division pairs with subtraction. So log base 4 of 64 minus log base 4 of y. And then I look to see right there, I can simplify that. The exponent of 4 that gives me 64 is 3. We can't do anything with that y there in that next expression, so just got to stop there. Again, I've got a quotient rule. I'm going to start with that quotient rule. So natural log of e to the 5th minus natural log of 11. And I see right here I've got an exponent, so I'm going to use my power rule on this first expression. So now I've got 5 times natural log e minus natural log of 11. And right here, natural log e, what's the exponent on e that gives me e? Well, that's 1. 5 times 1 is 1 minus natural log of 11. Alright, and then this last one on this page, again I've got a radical. Oh, you know what? I used the quotient rule and then I used my power rule. Let's note that. We used the quotient rule and then we used the power rule here. Okay, so for this one, I've got a radical. I'm going to write this as natural log of x to the 1/3 power. Replace my root with an exponent. And now when I have it as an exponent, that's when I can use my power rule. So 1/3 natural log of x. Since I don't know what x is, I can't do anything else, and I'm done there. Okay, that was expanding and simplifying as we can. Let's talk about using these rules for logarithms to condense, to put things together. On 7 through 11, we're going to condense each statement to a single expression and simplify anything we can simplify. Okay, so we've got 2 log expressions, same base, separated by addition. Addition is pairs of multiplication, so we're going to use our product rule there. We can multiply the arguments. So I've got log of 25 times 4, and 25 times 4 is 100. So I've got log of 100. Well, what's my base there? The base isn't written. It's log log. So the base is 10. And I'm asking the question, what is the exponent of 10 that gives me 100? Well, 10 squared gives me 100. Okay, so this one gets interesting. Let's look at this one. We've got 2 log statements. This has got a lot going on in here. I don't have a rule for that, though. I'm adding in the argument. There's no rule for that, so that's not going to change. This coefficient becomes a power. This coefficient becomes a power. So I've got natural log of x squared plus natural log of x plus 5 to the 1/3 power. Now, I know I could rewrite this as a cube root. I also know that I'm adding an addition pairs with multiplication. So I used my power rule. Now I'm going to use my product rule. And I'm going to say, okay, x squared, those are my arguments right there. So natural log of x squared times x plus 5 to the 1/3. Now, I can't combine those because they're not like terms. There's nothing else I can do in there. I can leave it like that, or I could choose to rewrite this as a radical and say natural log of x squared times cube root of x plus 5. That's fine too. Either way, it's great. Okay, let's look at the next one. I'm subtracting, and I have coefficients. So I'm going to start by applying the power rule. This one gives me natural log of x plus 6 to the 4th power minus natural log of x cubed. And now I'm going to apply that quotient rule. Subtraction pairs with division, so that becomes natural log of, well, that's positive in my numerator, x cubed goes in my denominator. So natural log of, and then that big messy argument there. I'm running out of space, but we'll keep it color coded so maybe it makes sense. We've got 3 statements here. Each of them has a coefficient, so I'm going to apply that power rule first. So I've got natural log of x cubed plus natural log of y to the 5th minus natural log of z to the 6th. Now inside this, I've got addition that pairs with multiplication, and I've got subtraction that pairs with division. So I'm going to use both the product and the quotient rules there. These two are being added, so when I write it as a single natural log statement, those 2 arguments go in my numerator, x cubed y to the 5th. The thing that's being subtracted, that argument goes to the denominator. And that's it. Alright, tackle number 11. Pause the video, try number 11, and see how you do on your own without any help. There's the answer. I'm not going to take you through the steps. Go back and look at number 10 if you didn't get the same thing I did, and see if you can figure out what went sideways, what you need to work on. Alright, we've got 3 or 4. Let's see if we wrapped around on the next page. We've got 3 big problems. Expand or condense as necessary. Simplify anything you can. Let's see what we've got here. We've got log base 3. We've got the first thing that I identify is division. So that's I'm gonna apply that quotient rule there. And I'm gonna say, okay, log base 3, and then my numerator is x minus 1 squared. And then minus log base 3, my denominator has 9z to the 3/2 power. So next step, my numerator, I guess I didn't really need those square brackets. This log base 3, I can apply my power rule there. That's my power rule. So I get 2 times log base 3 of x minus 1. Now, subtraction in that argument, I don't have a rule for that. So there's nothing else I can do here. Right here, though, I am multiplying there, so I can use my product rule to split this apart to 2 separate statements. Now, all of this came from the denominator. It's all being subtracted out. So I'm going to say minus log base 3 of 9 minus log base 3 of z to the 3/2 power. Okay, now I'm going to take a step back and see what else I can do. This first bit is set. There's nothing else I can do here. This next expression, though, what is the exponent of 3 that gives me 9? Well, 3 squared is 9, so that becomes minus 2. And then this last term, I can use my power rule and pull that out front. So I've got 3/2 log base 3 of z. I don't have any values to plug in for variables, so we are done. Now for this one, number 13, we've got base 5. Our numerator is x cubed y to the 4th. Our denominator is 125 times z squared. Pause the video, try that one. I'm just going to give you the answer. I want you to try it on your own, and then you can look to see if your answer matches mine. Have gotten 4 separate log statements, except that this third log statement right here, log base 5 with 125, simplifies to give you 3. These are both being subtracted because they both came from the denominator. These are both positive, being added because they came from the numerator. Number 14, instead of expanding, we're condensing. It's a lot like numbers 10 and 11. So I encourage you again to pause, start by applying your power rule. Think about what goes in the numerator and what goes in the denominator. And that should be what you end up with. Alright, one more quick page. We're going to talk about the change of base property. So a last property. What do we do when we don't have base 10 or base e? Well, we set it up as a ratio, change of base. Because we're going to set it up as a ratio, our rates balance each other out, and so even though they're the same base, our values come out to be the same. So we can either use common log button or we can use natural log button. It doesn't matter which one. But the base goes on bottom. That's the thing you have to remember. The base goes on bottom, argument goes on top, and we set it up as a ratio. Log of the argument over log of the base, or natural log of the argument over natural log of the base. For example, if I want to find log base 3 of 7, I'm going to use my change of base property to find log log, or you don't have to do it both ways, just one or the other, but I'm going to show you that they're the same. The base goes on bottom, the argument goes on top. So if you plug this into your calculator, now order of operations matters. So I'm going to say common log of 7, enter, divided by common log of 3. And I get 1.77 to 2 decimal places, about 1.77. If I do natural log of 7, enter, divided by natural log of 3, I get the same answer. Now you've got to use order of operations, parentheses, hit that enter button, something to make sure that you get the right value. Got some examples here. Let's go through these real quickly. Using our change of base property, base goes on bottom. I'm going to pick natural log first. Base goes on bottom, approximately, because I'm not going to be able to get an exact answer. If I can use common log or natural log, I get the same thing. Natural log 56, I divide that by natural log 3, round to 2 decimal places, 3.66 about. And on the next one, I'm going to choose to use common log just to switch it up. Base goes on bottom, argument goes on top. Common log 9 divided by common log of 0.2, get a negative 1.37 when we round it to 2 decimal places. Now, for these three, we're going to have to use our definition of logarithm first, and change the form. I can't solve for x in the exponent, so I can rewrite it in exponential form. Log, my base is 5.44. my argument is 2.3, and that is equal to the exponent. So you see what I did? I rearranged my terms, put it in log form, and now I can use my change of base property. Same thing's going to happen here. I'm going to use the definition of logarithm. Base 10, so I don't have to write that, of 3.91 is equal to my exponent x. Same thing here. Log base 7 of 410 is equal to x plus 2. So once I figure this out, I'm going to have to subtract 2, move that over to finish solving. Alright, change of base formula here. This is natural log or common log. Base goes on bottom. 2.3. So if I do natural log of 2.3 divided by natural log of 5.44, I get 0.49. We're doing 2 decimal places, right? So x equals about 0.49. Now I don't have these written down on my paper, so if I make a mistake, you're going to have to email me. Common log. I got a button for that. Common log of 3.91. Boom. X is about 0.59 because I have to round it off. And then right here, I got to do an extra step, right? So let's do natural log of 410 over natural log of 7. And then to finish solving for x, I have to find that, and then I'll have to subtract 2 to finish solving for x. So let's do that. Common log, just because I chose it, 410, enter, divided by common log 7, enter, and then I need to subtract 2, and I get 1.09. X is about 1.09.